Hi everyone, Mr. Fortin is here with your notes number 2, different function types. Now I have written down here already the main ideas of these notes. I would write down all of these because if you're writing, it turns out you're kind of thinking about things and coming up with different ideas and maybe noticing things that you wouldn't notice if you just read along with me or tried to listen. So write these down with me together. Okay, in class, right, main ideas, there are a number of different families of functions that we will study this year. Now, we've seen a few previewed for us in class so far. These functions operate a little bit differently from one another. Some functions have a table that works a certain way. Some functions will have a graph that will look a certain way. So what we want to do in this video is begin the idea of classifying certain functions by what their tables do and what their graphs look like. And we've only really looked at this for 3 function families. Okay, so this is what this video is just recapping what those 3 function families we've seen so far, because we're going to see more functions like them, maybe not exactly like them, but functions that will behave pretty closely to this family, and this family. We might say, hey, it's part of that family because it follows these rules. Okay, here's a family that we saw today, the direct variation family. You guys probably saw this family in middle school quite a bit when you guys studied linear functions. When we see linear, right, we see that word line, right? We see that word line. A line in math, right, means a straight line. You need to be straight in math to be a line because if you have 2 points, there's only one line that you can draw connecting those two. Sure, there are curves, and we'll study curves later this year, but if you are a straight line, we say that you are a linear function. Here is where direct variation is a little bit different because direct variation, yes, this is a straight line. This is our graph of a direct variation function. Looks just like this, straight line here. What makes the graph unique is that it'll have a point at the origin, okay? Have a point at the origin. Direct variation family will have a point at the origin, and what the origin is the coordinate 0, 0. Remember, x is 0 here, and y is also 0. So where my x-axis and y-axis meet together, well, my x value is 0, my y value is 0. So it has a point at 0, 0. That's different than other linear functions because other linear functions, right, other ones, right, you might have a y-intercept that's not at the origin. It might look like this, right? If I shifted this graph up a little bit here, that's not direct variation. That's something different. That's just a normal linear function, okay? Direct variation are special because they have a point at the origin. And what you end up noticing here is that rise over run, we're increasing at a constant rate, right? We're increasing at a constant rate. And something interesting kind of happens with the numbers in the table for direct variation as opposed to linear functions is if I have a point at 0, 0 and I'm increasing here, this is one thing to notice here. Point is at 0, 0, okay? And my growth is constant, right? Growth is constant, linear, it's consistent. My constant growth means I have a change number. As x increases by 1, number of signatures increases by 1, the time, right? It took me exactly, right, in this data that we gather, here's pretend data, it took me approximately, right, or exactly 0.5 seconds every single time I wrote a signature. So it took me 0 seconds to write one signature, 0.5 seconds later to draw another signature, 0.5 more seconds to draw my second signature. Okay, every signature takes 0.5 of a second according to this data. So what we have here is down here, a constant growth. And this is something called slope. We're going to study this later this year when we get really into linear functions. Okay, so this is one of the things that make direct variation special. Have you written that down in your notes? We'll have a point at 0, 0, the origin, and as I go from 2.5 to 3, I'm adding 0.5. As I go to 3 to 3.5, it takes me 0.5 seconds per signature, so my growth is constant. Okay, there's an attribute there. Another interesting thing about direct variation is that the y values directly vary, right? Directly vary from the x values. Now, this is kind of complicated here. So try to look at this one here. The kind of interesting thing is if you spot a pattern between the y values here. Look, this is my x value, this is my y value, at least on my axes, right? Number of signatures goes up by 1. My time only goes off by a half each time here. But anyways, the x and y values are proportionally related. So I'm going to write this one down here. Okay, x and y coordinates are proportional. They directly vary. It's called the direct variation family. Okay, these 3 things are going to be true. What does that mean? Well, if you look at the y values, okay, you look at the y values, they're all exactly half, exactly half the x coordinates. That's kind of neat, right? This is special, but for direct variation functions. Not going to be special about all linear functions, but it is. If I have the only exception, of course, is the origin. But if I have a y-intercept of 0, 0, and I have a constant slope, then I'm going to know that my y values here. Look, if I divide this x value by 2, I get 5. If I divide this x value by 9, I get 4.5. If I divide this x value by 4, I get 2. Right? So I divide that by 2, I get 4. Anyways, it directly varies. But I can set up a ratio of the x value to the y value, right? A ratio in math is just a fraction, right? 8 divided by 4, that equals 2. That's the same thing as 9 divided by 4.5. 9 divided by 4.5 would also be 2. 10 divided by 5, that would also equal 2. So they directly vary. They have a constant ratio, okay? X and y coordinates are proportional. Those are the 3 notes there. Okay, inverse variation. This was the second function that we saw when we did or first one that we saw in the lesson, that this was the hot tub design here, okay? So inverse variation family, it's kind of nonlinear function, okay? Why do we know that this graph is nonlinear? Well, it's curved, okay? It's curved here. So when we see nonlinear, what you're thinking in terms of describing that is a curved function, okay? Curved. Right? Nonlinear kind of means curved. It's not a line. Okay, inverse variation family, they're going to be nonlinear functions. Okay, and this is the pattern here. Okay, so what's the pattern? Okay, the x and y coordinates multiply to the same number. A fancier way of saying that is that the x and y coordinates here are my coordinate pairs. They would multiply to the same constant. Check this one out here. This is one way that you can tell that your graph is inversely proportional. Your function is inversely proportional. Your table is inversely proportional. Is that if I take 1 and I multiply 1 times 36, I get 36. 2 times by 18, I get 36. 3 times by 12, I get 36. Okay, so it's very similar to direct variation in that I take my x, I divide by y, I get a constant, I get 2. Take my x divided by y, I get 2. Here is that I take my x and I multiply my y, I get a constant, right? I multiply that, I multiply, I get to the same number, right? Constant means being the same thing, right? 4 times 9 is 36. And that works through. Okay, so the x and y coordinates multiply the same number. And another observation that I'm sure many people had is that my x and y coordinates will kind of flip-flop later. Okay, if the meaning here, check this one out, is that if I have 136 as one of my coordinates here, 1, x is 1, y is way up here at 36, that's one of my coordinates on my graph, then I'm also going to know that when x is 36, I'm going to have a y point at 1, right? Y coordinate of 1 here. So if 136 is a point, 136 here, then 36, 1 is also a point here. So I'll add that onto our notes here. That the x and y coordinates will flip in table. That's another thing to notice here. So I got 136 there, 36, 1 there. Odds are it's inverse variation. 2 18s here, I got 18, 2. 3 12 is here, I got 12, 3. It's all patterns, right? All pattern is algebra. It's all about patterns, about noticing things, okay? Last but certainly not least, we have the exponential family, which is another kind of nonlinear function. What does nonlinear mean again? Well, nonlinear just means curved, okay? And this graph here, as opposed to this graph here, remember, ignore your x-axis, ignore your y-axis. What is the actual relationship that's being graphed doing? Well, it's a straight line in a direct variation. Just happens to go through the origin, goes through 0, 0. Well, it's a curve for inverse variation, and the coordinates get flippity-flopped here. Okay, 2, 18. I'm going to have 1 at 18, 2. Get flip-flop. Here, and it ends up being curved, so it's nonlinear. Okay, here's a relationship, the exponential family, where we're also going to end up with a graph that is also curved. This is a graph of an exponential function. We're going to study that in Chapter 7. Okay, so exponential family, another kind of linear function. And what I might want to do is describe its shape right now. Okay, one thing we say in class is looks like a backward J. Okay, that's what it looks like, right? Doesn't a J look like this? Well, actually, this just looks like a J. Looks like a J. Okay, we're going to look at backwards J's for exponential functions as well. But it looks like a J without this thing here. okay, without this thing here. So maybe do a J without the top. Okay, sometimes we describe what things look like by talking about what letters they look like. Okay, it looks like a J. In the graph, of course, this is my graph. This is my table. Okay, looks like a J. I might also say that looks like all my Y values are bigger than 0. Okay, that's an interesting thing. All Y values, at least for this one. Maybe I'll put that here because we're going to study exponential functions later. That will be true for all exponential functions. But it looks like a J. What we might want to say is that growth is not constant, right? Is not constant here. It was constant growth in direct derivation. That's why we have a line here. Growth is not constant. Because how does growth work for exponential functions? Well, what pattern did you guys notice for the local crisis, the illness that we had here? We have day numbers are increasing by 1. How are the number of infected people increasing, right? When each person was getting 2 people sick, and that would keep repeating. Well, that would mean if we go from 1 person, we would have 3 people sick. So this was multiplying by 3, right? Multiplying by 3 was the great growth, right? The great growth here is not constant. It grows. So exponential functions, we'll notice this year, especially when you do chapter 7, is that growth is by multiplication. Okay, x goes up by 1, my y values, right? X goes up by 1, my y variable here is going to increase by a multiple, multiply by 3. Okay, so if I see this in my table, I'm going to know that this function has to be part of the exponential family. Okay, let me know if you have any questions. We're going to practice these and look at more of these function families all year. Algebra 1 really is the analysis of patterns and growth of numbers and change of numbers. And there's, of course, a whole bunch of change in our world. And I'm glad you're along with this ride. Message me if you have any questions. Thanks, guys. Bye.